So here we go with video 2 of Lesson A. In this video, we will be focused on the dynamics of uniform circular motion with the goal of fulfilling this learning target here. So we're going to be looking at motion in horizontal circles and vertical circles and looking at the forces involved in uniform circular motion. So here we go. So last time we determined that objects that are in a uniform circular motion are accelerating because their direction is constantly changing. So because objects traveling in uniform circular motion are accelerating, Newton's second law states that they must have a net force acting on them. So what is that direction of that force? Well, let's consider this fellow right here. He's a hammer thrower. And what he does is he takes that hammer, it weighs probably 30 pounds, and he spins it around and tries to throw it as far as he can. So as he's spinning round and round, he has to pull on the handle of this thing as hard as he can toward himself, toward the center of the circular path. You can simulate this easily by just attaching something to a string and spinning it around over your head. So this hammer, this object, gets accelerated toward the center of its circular path. We just learned that this is called centripetal acceleration. The force that brings about this acceleration is called the centripetal force. The centripetal force is the net force that acts toward the center of an object's circular path. So remember, centripetal means center seeking. So the centripetal force changes the direction of the object's velocity vector, and without it there'd be no circular path. The term centripetal force is merely just a convenient name for the net force that acts toward the center. So it's really important for us to understand that centripetal force is a net force, and it could be brought about by gravity, it could be brought about by the reaction force between control surfaces of an airplane with the air, that sort of thing. So several different types of forces could result in a net force toward the center of a circular path, which we would then call that net force the centripetal force. Right? So for the hammer here, or even when you twirl an object around attached to a string, the centripetal force is supplied by the tension in that string, or the tension in this hammer's handle. So how do we find the magnitude then of centripetal force? If we start with Newton's second law, F equals ma, and we substitute in our centripetal acceleration, v squared over r, we end up with mv squared over r. So the net force producing the centripetal acceleration is given to us by mv squared over r. It's important to remember that this is not on the equation sheet, but it is worth memorizing, so get it in your head. So what this is saying is a particle of some mass moving at a constant speed around a circle of some radius must always have a net force of magnitude mv squared over r pointing toward the center of the circle. Without that force, the particle is going to move off into a straight line tangent to the circle. So we have one basic equation for circular dynamics problems, this one above, which is just a version of Newton's second law. Here we're talking about a net force, and here we've got a mass times an acceleration. That acceleration is just a centripetal acceleration. So the techniques for solving circular dynamics problems are similar to those we've already dealt with Newton's second law. To prepare, you want to draw a picture where you sketch the motion, define the symbols, identify what the problem's trying to find. You write down the given information, what you're trying to look for. When you go to solve, Newton's second law for uniform circular motion is a vector equation. So some of these forces will act in the plane of the circle, some will act perpendicular to a circle, and some may have components in both directions. Let's kind of look at that. What this means is, if I've got something in a circular path, I'm spinning around a ball attached to a string, I can spin that around so that the string is completely flat in the plane of the circle, so that all of the tension on that string is directed toward the center. So the full force is toward the center of the circle. I could also take that string, say, and spin this ball so that the string comes here and the ball makes a circular path this way, right? So in this case, it's going to be a component of this tension that acts toward the center of the circle. So this would just be a component of it. So if you've ever seen like the guys, you're spinning a rodeo rope around, that's the kind of situation I'm talking about with this diagram here. So if it's a component of a force that acts toward the center that provides that centripetal acceleration, we'll have to make sure that we focus on that and split those components, those forces, into their components. So the important thing that we do is we make sure that the net force toward the center of the circle is mv squared over r, while the net force perpendicular to the circle is 0. The components of the forces are found directly from a free body diagram, and depending on the problem, we'll either use that net force to find the speed, then use kinematics to find frequencies or angular velocities, and then use circular kinematics to determine the speed, then solve for unknown forces. So let's look at a few examples. Here we have an energetic father places his 20-kilogram child on a 5-kilogram cart to which a 2-meter long rope is attached. He then holds the end of the rope and spins the cart and child around in a circle, keeping the rope parallel to the ground. If the tension in the rope is 100 newtons, how much time does it take for the cart to make one rotation? So in this picture, we have a top-down view. The dad is spinning cart in this direction. His tangential velocity, his linear velocity, is going off in this direction. So we know the mass of the child, we know the radius of the circle, we know the tension in the string, in the rope, and we want to find the period in seconds. So on a free body diagram, which shows an edge-on view, we placed the x-axis in the plane of motion. So we have the weight, normal force of the cart. So this is the cart we're looking at. We've got the weight of the cart, the normal force, and then here's the tension along in the direction of the net force. So there's no net force in the y direction. It's perpendicular to the circle. So the weight and the normal force are equal and opposite. There is a net force in the x direction, though, toward the center of the circle, as there must be to cause this centripetal acceleration of circular motion. Only the tension force has an x component, so my net force in the x direction is equal to the tension. And because this is a centripetal force, that tension will be equal to mv squared over r. Solving for this linear velocity, then, we end up with 2.83 meters per second. So as we've learned previously, the kinematics equation for linear speed is this right here, which, by the way, is the same as our constant velocity equation we've had previously, right? It just, in this case, here we're talking about a circular path, so we have a circumference there. So we go to solve this then for our period, and we get 4.4 seconds. So let's look at another example. What is the maximum speed with which a 1,500 kilogram car can make a turn around a curve of radius 20 meters on a level unbanked road without sliding? So this radius turn is what you might expect at like a major intersection in a city. So we start with the visual overview. The car moves along a circular arc at a constant speed for the quarter circle necessary to complete the turn. The motion before and after the turn is not relevant to the problem. The more interesting issue is how a car turns a corner. What force or forces can we identify that cause the direction of the velocity vector to change? So imagine you're driving a car on a completely frictionless road, such as super icy. You would not be able to turn a corner. Turning the steering wheel would be of no use because the car would slide straight ahead, in accordance with both Newton's first law and the experience of anyone who's ever driven on ice. So it must be friction that somehow allows the car to turn. So the top view of the tire in this picture shows the force on the tire as it turns the corner. If the road surface were frictionless, the tire would slide straight ahead. The force that prevents an object from sliding across a surface is static friction. Static friction pushes sideways on the tire toward the center of the circle. How do we know that? So how do we know that the direction is sideways? So if the static friction had a component either parallel to the velocity or opposite to the velocity, it would cause the car to speed up or slow down. Because the car changes direction but not speed, static friction must be perpendicular to the velocity. So the static friction causes the centripetal acceleration of circular motion around the curve. So with this in mind, we draw a free body diagram from behind the car showing the static friction force pointing toward the center of the circle. So going around a curve in a car, it is the static friction of the road on the tire that provides the centripetal force to allow us to change direction as we go around the corner. So Newton's second law tells us that our net force is equal to mass times acceleration. Because we're going around a circle, we know that this is a centripetal acceleration, so we have mv squared over r. That centripetal force is provided by the static friction force, so our static friction here is equal to mv squared over r. So the only difference between this example and the previous one is that the tension force toward the center has been replaced by a static friction force toward the center. So there's three forces acting on this car. There's the weight force, the normal force, and the static friction force. Because there's no vertical motion, the weight and the normal forces are equal and opposite. So the net force toward the center of the circle is the force of the static friction. Now, remember, static friction has a maximum possible value, which is equal to coefficient of friction times the normal force. Normal force is equal to the weight in this case because there's no acceleration in the y direction. So we can set all this equal. So because the static friction force has a maximum value, there will be a maximum speed with which the car can turn without sliding. This maximum speed is reached when the static friction reaches its maximum. If the car enters the curve at a speed higher than the maximum, the static friction will not be large enough to provide the necessary centripetal acceleration. The car will slide, which is what those guys do that try to drift around corners all the time. So when we put in all our values, we have this possible problem of what is the coefficient of static friction between rubber and the road. We can look up that in a table if it's not given in the problem, and there's a table on page 151 of your textbook if we run into a problem where that coefficient of friction is not given to you. So we plug in our values. We find that rubber on concrete is a coefficient of 1, mass of the car, g, mass of the car, radius for circle, and we end up with a velocity then of 14 meters per second. So this is the maximum velocity that this car can go around that corner. So now let's think about apparent forces in circular motion. So what we have in this figure here is we've got the inside view of the graviton. That's a carnival ride that spins riders around in a large cylinder. People get stuck to the inside wall of the cylinder. And as you probably know from experience, the riders feel like they're being pushed outward into the wall. But our analysis has found that an object in circular motion must have an inward force to create the centripetal acceleration. So how can we explain this apparent difference between what we know to be true versus what we experience? You may have heard of the centripetal force before you studied physics. It's possible. Most people don't use the term. Instead, they talk about something called a centrifugal force. So what in the world is that? Okay, we've seen the word centrifugal force. Now, forget about it. It's really bad form for a physicist such as you to use such a naive term. Here's the deal. The centrifugal force is the thing that people blame for the feeling that things seem to be pushed away from the center of spin during rotation. If you place a coin on like a turntable and spin it really fast, what happens to the coin? In your mind, picture that coin flying straight away from the center of the record. The individual who has not studied physics would say that this was because of the centrifugal force. So here's an important concept. The centrifugal force is a fictional force. There is no actual force that is pushing away from the center of a rotating system. You feel this centripetal force when you're a passenger in a car that makes a turn. When the car enters the turn, you feel like you're being pushed into the door, away from the center of the circular path the car is making. So you think, hey, I'm being pushed into the door, so there must be a force pushing me away from the center of the turn. That's exactly how you feel at any rate. So what's happening here is you as the passenger want to travel in a straight line path at some constant speed, which is in accordance with Newton's first law. The car, however, has different ideas. It wants to go in a circular path. Its tires pushing it toward the center, exerting a force to make it all happen. So the car changes direction, but you, the passenger, do not. No force is acting on you, so you go forward in your original direction until you push into the door, which then pushes you toward the center, and you go in a circle as well. The third law rears its head. You push into the door, and the door pushes into you. You feel like you're being pushed into the door, even though there's no real force doing this. It's just the reaction force to you pushing into the door. And this is what a lot of people mistakenly call the centrifugal force, the sensation of being pushed away from the center. So if, say, the centrifugal force was real, say, for example, there was a force pushing you away from the center of the circular path, then if the door were to suddenly pop open, you'd fly straight away from the center of the circular path. But of course, that doesn't happen. If the door were to fly open, you would travel in a tangential path. The centripetal force is real, then the centrifugal force is not. So now let's think about apparent weight in circular motion. We talked about apparent weight with linear motion by using elevators. So now let's think about apparent weight using in regards to circular motion. So if I spin a bucket of water, say in a vertical circle fast enough, the water will stay in the bucket. Maybe you've tried that or seen it done. So what's the deal? Does the spinning something in a vertical circle somehow cancel out gravity? Well, no. Gravity is a force that cannot be stopped or canceled. It's always there. So anytime you have the appropriate masses, the water does fall, but the bucket falls with it and catches it. Now this only works if the bucket's moving fast enough to catch the water. If the bucket's too slow, then the water will fall out of it. Now the same thing happens if you are in a roller coaster, say, that goes in a loop. Now, if you've ever ridden in such a thing, you know that your sensation of weight changes as you go over the crests and through the dips and around the loop. To understand why this is, let's look at the force on passengers going through this loop. And to simplify this, we're going to assume that the speed of the car stays constant as it moves through the loop. Part B of the figure here shows the passenger's free body diagram at the top and bottom of the loop. So we're going to start by examining the forces on the passenger on the bottom of the loop. So the only forces acting are the weight and the normal force of the seat pushing up on the rider. So remember, a person's apparent weight is the sensation of weight. It's the magnitude of the force that supports a person. Okay? So here, the seat is supporting the passenger with this normal force, so our apparent weight is equal to the normal force when you're just standing or just sitting in the car. So, based on our understanding of circular motion, we can say that she's moving in a circle, so there must be a net force directed toward the center of that circle, currently directed straight above the head from the bottom of the loop, if we're at the bottom of the loop, to provide the centripetal acceleration. The net force points upward, so that must mean the normal force is greater than the weight. And her apparent weight then is equal to the normal force. So her apparent weight is larger than her true weight, so she feels heavy at the bottom of the circle. So basically the normal force has to exceed the weight force to provide the net force she needs to turn the corner at the bottom of the circle. And to analyze this quantitatively, we note that the force vectors in this figure, that the magnitude of the net force at the bottom of the loop is given by this. The net force provides the centripetal acceleration, so we can say that that net force is equal to normal force minus weight equals mv squared over r. And then when we go to solve for that apparent weight, we find that the passenger's apparent weight is larger than the true weight at the bottom of the circle, which agrees with your experience when you go through a dip in a roller coaster or as a passenger in a car going down a small hill. So now let's look at the roller coaster car as it crosses the top of the loop. So things get a little trickier there. Where the normal force of the track pushes up when the car is at the bottom of the circle, it pushes down when the car is at the top and the track is above the car. So this is the case right here. When this car is at the top of the loop, then our normal force points straight down as well as the weight. So this same free body diagram would apply for a bucket of water we spin around our head. The question is, how fast must the car keep going to keep it from falling off the track? Or how fast would we have to spin the bucket to keep the water from falling out? So the minimum linear speed for this is called the critical velocity. That's the minimum velocity for an object to travel in a vertical circle and maintain its circular path against the force of gravity. So we know the centripetal force is mv squared over r, and we know weight is mg. If we set those equal to each other, we can solve for velocity, and we get the critical velocity, v equals square root of gr. Now this same thing is needed for satellites in orbit around the Earth or planets in orbit around the Sun. They also have to travel at a critical velocity, and we'll be looking at that in Lesson B next time. We'll see you in class.